Alright, so now we're doing linear regression. Basically, it's when you take a scatter plot and you get the best line of best fit. Alright, so let's see how we do this. You're going to use Excel to get our regression equation. So here's some data which you can copy into Excel. So you may need to open Excel right now and pause the computer for a second, enter this data. Alright, so I'm going to switch over to my Excel. Here I have it. I just cut and pasted the little table there. So I would start entering all this data, but actually I don't have to because I actually saved it already. So here we go. And then also it's good to give your everything titles. So here's age in months. Here is average height. That's in centimeters. And then up at the top I give it an overall title. So mean height versus age. Alright, so it's not necessary for the calculations, but it makes it look a little nicer. So here's all you do. Make sure you pay attention to this part. I'm going to highlight, including the text, because it knows that those are titles. I'm going to highlight my numbers. I'm going to go up here to where it says home, layout, all that stuff. If you don't see those things, you click on it twice and it's there. So we're going to go to charts, and I want, oh good, it doesn't give me what I want here. I want marked scatter, so we go to other. Marked scatter is what we're looking for, so you want this one. Okay, click that, and it makes your chart for you right there. Okay, it automatically starts with an X scale of 0, and you can change this all around. So what I want to do is maybe I don't want to see all the way to 0, so I format the axis, and I'm going to have it start at 10. Okay, so that looks a little bit better. Okay, that's fine. Now here's the key. To get your regression line, you click on one of your little data points here. You have to right click on it. So I right click on it, see how it's selected? And then what I'm going to do is I'm going to add trend line. Okay, so when it does that, this box pops up, and there's all different types of data. So not everything is linear, but we're dealing with linear. It strongly suggests a linear relationship. So we're going to go with linear, and then we're going to go with options. Okay, so we want options. And what you're going to do is you want to display equation on chart and display the R squared value. So make sure both of these are clicked. Okay, once you've done that, you see it popped up over here. So now we hit OK. And then that's it. And you can do all sorts of different things to play with the font of this, make it larger, smaller, whatever. You can have that box or not, doesn't matter. Obviously you can resize everything. If you enter this into a Word document, the Word document knows all the stuff that Excel does, so you can actually still play with the chart. I'm going to copy this and put it in my slideshow. So Smart Notebook does not know what I just did here. So here we go. Now let's analyze some of this using the similar stuff we did for analyzing scatter plots. Okay, so based on what we did, if you entered the data correctly, you should have got the exact same equation as me, because this isn't like the scatter plots or the line of best fit where we get kind of close. This is exact. So our equation is y equals 0.64, no, my bad, equals 0.6343x plus 64.928. And I forgot to tell you what this was. This is, I guess in like Egypt or something. There was some recording of data. So age is in months. Make sure you realize this is months, so it's like 18 months is a year and a half old. Heights are in centimeters. And I don't remember what the study was for. So what is the slope of the regression line, and what does it mean in the context of the equation? Well, the slope of our regression line is right here. So that our slope is a 0.6343. Alright, and what does it mean in the context of our equation? That means for every increase in the x, we have this many units increase in y. So for every increase of month and age, so for every increase of 1 month in age, the height increases. So the average height of our individuals increase by 0.6343 centimeters. So basically they're growing 0.63 centimeters per month. Our R value. Now I want you to notice right here, this gives us R squared. Alright, that's because we can use R squared for any of those things, but for any type of model. But for linear, it's actually more better to look at R. So what we're going to do is, since R squared is this number, what we need to do is take the square root, right? We have to unsquare it. Alright, since we want R, we don't want R squared, we got to unsquare it, which means taking the square root. So what we're going to do is, I'm going to do that on my calculator right now. Square root of 0.98631, and that gives me 0.9931 is plenty of significant figures. Okay, so that is a wicked good R value. Okay, so all R values are between between -1 and 1. Alright, so our R value tells us how good the data matches the line. How close is it to being? If all our data was in a perfectly straight line, we have an R value of exactly 1. Or if our data was going downhill, so if it was a negative correlation, so for every increase in x, we went down in y, so it was like a negative slope, perfect R value would be -1. So R is always between -1 and 1. Alright? I mean, I guess you can put the equals too, but chances are it'll never be actually equal to a perfect data. So this gives us a very strong correlation because we're very, very close to 1. Okay, about 0.95 and above is very strong. Moderate would be anything between around 0.5 and 0.95. Weak is anything less than that, or anything less than like a quarter. 0.25 is, there's not really any correlation. And it's positive because see how that's a positive number here. Now actually this will always be a positive number because we're taking a square root here. So it's positive because our slope is positive. Okay. So based on the equation, what is the predicted height for a 36-month-old? Well, just go to your calculator, plug that in. 0.643 or 6343 times 36 plus blah 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 gives us 87.76. Does that make sense? So why don't we take this and convert it to inches? So we have to divide by 2.54. And that's almost 35 inches. That rounds up to 35 inches. Should a 36-month or a 3-year-old be about 35 inches or about 3 feet? Yeah, that makes sense, I guess. Alright, what's the y-intercept of our regression equation? Well, our y-intercept is right here. Alright, so the y-intercept is 64.928. So our y-intercept is when the x value is 0. So if we were to continue that back and let the all the way back to x equals 0, since we have age and height, when the age is 0, that would be like when it's born, right? So we're saying that that's what it stands for in the context of this problem is at age 0, or when it's born, what is its initial height? So let's look at what's 64.928 and divide that by 2.54 to get inches, because I don't really know centimeters that well. Alright, so 25.5 inches. That could be a newborn. It's a pretty big baby, I think, actually. I think it's bigger than most. So maybe this model doesn't extrapolate backwards perfectly. Maybe, you know, babies grow a real lot at the beginning. They get longer really quick and then sort of come out to this consistent growth pattern. So maybe it's not linear as you get back towards newborns. But does it make sense? Sure. Basically, for a question like this, it depends on how you justify your answer. Alright, so if you say that 25 inches is way too big, you know, my baby was like 19 inches when she was born, that's 6 inches bigger, well, then that's a good justification. You could say that it doesn't make sense, as long as you're showing some thought here and it is applying to the problem. What is the x-intercept? So what you would do here is you would just take your equation. The x-intercept is when your height is 0, so that's when the y value is 0, so you just plug in 0 for y. And that equals this. So then I subtract this from each side. I'm being a little lazy here because I'm running out of room and time. I don't want to waste yours or mine. So we got negative 64.928 equals 0.64343 x. So divide both sides by that. Whoa. And what do we get? Alright, and that equals 102. So what does that tell us in the context of the problem? So I just want to resize my page. Okay, I guess not. So when y is 0, it means when would they have a 0 height? Okay, so that doesn't really make sense because babies are born not with a 0 height. They're around 20 inches long, and even in the womb, you know, 9 months of growth is they're changing always. So height isn't necessarily going to be a consistent linear pattern. This says, oh, this is a negative, my bad. This says at negative 102 months, so 102 months before they're born, they would be 0 height, and that clearly does not make sense because 102 months is almost 9 years, and that would be, women would not like that. That would be a very long gestation. I think that would be rough. So, no, this does not make sense. And there's really no way to justify that and say that it makes sense. Alright, so just a little discussion here on residuals. So we've done all the analysis. Hopefully you watched how I got it from the Excel equation. It's just highlight the data, tell it to go to a marked scatter, and then once you do that, you right click on the point and tell it to add trend line, and make sure that you tell it to show the trend line. Okay, and if you right click on any of these things, you can format anything you want here, right? So format trend line, format text. You can, you know, make this all kinds of cool looking if you want. Like that's what I did here, is I just changed a few things. So lastly, we're going to talk about the residuals, which is a pretty simple concept, okay? So let's look at